Hello everyone. On this video we will be covering line integrals. Alright, so before we get started, I want you to remember that you have the vector valued function, which is x of t I plus y of t times a j vector for a value of t that's between some a and b. Alright, now that is considered smooth if the first derivative with respect to x and the first derivative with respect to, well, derivative of x with respect to t and derivative of y with respect to t are both continuous. Didn't need that comma there. On that same interval. And of course, both of them are not equal to 0. Okay, one could be equal to 0, but not both. Okay. Now, of course, the same applies for 3 dimensions. Okay, so if your vector valued function is some function of t times I vector plus some function of t times a j vector plus some function of t times the k vector for that same interval. Now that will be considered smooth if of course the derivative of all 3 were continuous on that interval. Okay. dy dt and dz dt are continuous on the interval from a to b and not all equal 0. Okay, that means that one can equal 0, 2 of them can equal 0, but all 3 of them cannot equal 0. Okay, and also I want you to think about the formula for arc length in space. Remember, from a to b, that's the square root of x prime of t squared plus y prime of t squared plus z prime of t squared. Of course, that's with respect to t. Okay, so remembering all of those will lead us into the evaluation of a line integral definition. A line integral as a definite integral. Alright, so what if we let f be a continuous region containing the curve C? Be a continuous region, well, continuous in a region. I don't know why I put A, be continuous in a region containing a smooth curve C. Okay. Now, if C, our curve, is given by our vector valued function for 2 dimensions, plus y j, of course, where t is between some values a and b. And that means that the integral with respect to your s value is equal to the integral from a to b f of x of t, y of t, and that's going to be multiplied by the square root of our arc length, x prime t squared plus y prime of t, and instead of that I'll put squared. Okay, so instead of the parentheses I'll put rectangles around here, just to show that entire thing is squared. Of course, that's with respect to t. And also, of course, you have to have the 3-dimensional definition of it. Let's say if your curve is given by your vector valued function, which is in 3 dimensions, plus z of t times the k unit vector. Okay, now if that's the case, of course your integral f of x, y, z will be equal to the integral from a to b f of x of t, y of t, I put g for some odd reason, z of t, times the square root of x prime of t squared plus y prime of t squared plus z prime of t squared. Uh-oh. We kind of clean that up a little. Running out of space. Alright, that is squared. There we go. And of course that's with respect to t. I don't know why I continue to do that and waste all that space at the beginning, then I have to squeeze in at the end there. Bad habit. Need to shake it. Alright. So, if you are still writing, feel free to press pause. Excuse me. But we're going to go ahead and move on to our first example. Okay, so what if we want to evaluate the line integral? Okay, so the integral, let's say x minus y with respect to s, with the curve that is represented by our vector valued function, which is equal to 4t times I unit vector plus 3t times the j unit vector. And that is from t is equal to 0 to t is equal to 2. All right. So this is how you would approach this problem. Okay, so we know that our curve r of t is equal to 4t I plus 3t j. That means r prime of t is equal to 4i plus 3 times your j unit. Okay. So looking at our formula, we have the integral from a to b, f of x of t, y of t, times the square root. Run out of pencil lead here. There we go. Okay, so we have x prime of t squared plus y prime of t squared with respect to t. Alright, now remember, this is your x of t here. And this is your y of t there. Which means this is your x prime of t, makes this your y prime of t. Okay, so what are you going to do? Well, of course, because you're looking for your function with respect to t, you're going to replace x with x of t and y with your y of t. Okay, so that means up here, you're going to have the integral from a to b, so that's your a to b, so from 0 to 2. This is your f of x, y, so instead of x, you're going to put your x of t, so that's 4t, minus, instead of y, you're going to put your y of t, so 4t minus 3t times the square root of x prime of t squared, so your x prime of t is 4. So that's 4 squared plus your y prime of t is 3. 3 squared. Shorten that up a little bit. With respect to t. Okay. Once you get everything you have, all of your components, you just go ahead and start integrating. Of course, we can simplify this. 4t minus 3t is just t. So integral from 0 to 2, that's just equal to t. And this is actually equal to the square root of 25. Okay, so here you have square root of 25 is 5 times t, so you have 5t. Here's just 5t with respect to t. Okay, so of course when we integrate that, we have 5t squared over 2, which is from 0 to 2. Okay, so you have 5 times 4, which is 20, so that's 20 over 2. You plug in 0, you get 0, so we end up with 10. Alright, so if you are still writing, feel free to press pause, but we're going to go ahead and move on to our next example. Alright, so let's say for this example we wanted to evaluate the line integral. Okay, so if we have x squared plus y squared plus z squared with respect to s, with the curve represented by, say, sine of t times the I unit vector plus cosine of t times the j unit vector. I probably could have moved that down a little more. Let me move this c up some. There we go. Plus 8t times the k unit vector. And that's for the intervals t between 0 and pi over 2. Alright, so just like before, Now r of t is equal to sine of t plus cosine of t times your j unit vector plus 8t times your k unit vector. All right, take the derivative of that. You know that r prime of t, derivative of sine is cosine, so you have cosine of t times your I unit vector. Derivative of cosine is negative sine, so we have minus sine of t times your j unit vector, plus, instead of 8t, that just becomes 8 times your k unit vector. Alright, so just like before, I'm just going to write the formula out. So f of x of t, y of t, z of t times the square root of x prime of t squared plus y prime of t squared plus z prime of t squared with respect to t. Alright, so we know, of course, that this is our x of t, this is our y of t, this is our z of t. So we have our x prime of t, that negative sign is our y prime of t, and that's our z prime of t. Okay. Now, if you forget the negative for this one, don't worry about it, because as soon as you square it, it's going to be positive anyway. So even though it's good to be conscious of it, that's one mistake you can actually live with this formula. So don't stress too much about it. All right, so you have x squared. Remember, you're going to replace x with x of t, y with y of t, and z with z of t. Okay, so you have x squared, which would become your sine of t squared. Okay, so that becomes the integral from 0 to pi over 2 sine squared t, and your y squared become y of t squared, so that's cosine of t squared, cosine squared t, and your z squared will become 8t squared, so 8t squared will be 64t squared. Okay, and that's times the square root of x prime of t squared, so that's cosine squared of t, your y prime of t squared, that's negative sine, well, I'll just put plus sine squared of t. Since you know the negative and negative will give you positive anyway. So instead of writing an entire line out, we have sine squared of t plus 8 squared, so your z prime of t squared will be 64 with respect to t. Okay, so just like before, you know, sine squared plus cosine squared is equal to 1. Same thing here, that's equal to 1. So we get from 0 to pi over 2, 64t squared plus 1, or you put 1 plus 64t squared, doesn't matter, times square root of 64 plus 1, which is square root of 65. Of course, with respect to t. Alright, so we can go ahead and move that square root of 65 up to the front, just to get that out of the way. And we can go ahead and integrate those two, so the integral for 1 with respect to t is just t. And 64, that's 64t to the third over 3. And of course, that's from 0 to pi over 2. so finishing this one off, we have square root of 65 times pi over 2 plus, here we have 64 pi over 8, and that over 3, so that would give us 8 pi to the third over 3. Of course, you plug in 0, you just get 0 plus 0, so we can go past that. Okay, so that would be square root of 65 pi, once you simplify it in there, over 6 times 3 plus 16 pi squared. Alright, so it's pretty straightforward once you plug everything in. Okay, so if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next example. And this is, of course, using this formula to find mass. Okay, so if we want to find the mass of a spring in the shape of a circular helix, okay, our vector valued function is equal to 1 over square root of 2 times cosine t plus sine of t plus t times your k unit vector. And of course, that's on the interval from 0 to 6 pi. Nope, yeah, almost. Okay, where the density of the wire is rho x y z is equal to 1 plus z. All right. Okay, so just like before, we start out writing our vector valued function. 1 over square root of 2 cosine of t times I plus sine of t times your j unit vector plus t. Why did I do that? Times your k unit vector. There we go. And we find our derivative. So our prime of t is 1 over square root of 2. You have negative sine of t plus cosine of t plus, you can put 1 times k if you want to. You don't have to put the 1 there, of course. Okay, so of course, kind of should have given this more room, but we can use this up top. It's your x of t, your y of t, and your z of t. And of course, this is your x prime of t, your y prime of t, and your z prime of t. Alright, just like before, we go ahead and just plug everything in. But the only difference is here, we have to actually remember one thing. Okay, and that is that, we'll put the integral first before I do that. The integral from a to b of the magnitude for your vector value function with respect to t, this is your length of the curve. All right. So once you have that, you have to find the magnitude of our derivative, which is 1 over square root of 2. Okay, that's times the square root. Why I put the parentheses there, just out of habit. X prime of t, y prime of t, z prime of t. Okay, so that's negative sine t squared, which is just positive sine squared t. Cosine of t squared, cosine of squared t, plus 1 squared, which is just plus 1. Okay, so we know this is equal to 1. Sine squared, cosine squared is just 1. So that leaves you with square root of 2. So square root of 2 times 1 over square root of 2 will just leave us with 1. Alright? So it turns out we didn't really need that, because any multiple for that would just turn out to be 1. Okay. So we know that our mass equal our integral. So it'll be rho of x t, y of t, z of t with respect to s. Okay. So we know that's the integral of 1 plus z with respect to s. Okay. So if you notice here, we go from 0 to 6 pi. You have 1 plus z. We're just going to replace z with z of t. We don't have an x of t and y of t to replace here. So this just becomes 1 plus, remember that's over square root of 2. So that's t over square root of 2 with respect to t. Alright, so remember, replace z with z of t. Okay, so we go ahead and integrate each one of those terms. The integral of 1 is just t. And if we pull out the 1 over square root of 2, we have t squared over 2, so that's just t plus t squared over 2 square root of 2. Of course, that's from 0 to 6 pi. Okay, so if we plug in 6 pi, we end up with 6 pi plus 36 pi squared over 2 square root of 2. 36 and 2 can cancel out. Of course, we plug in 0, we get 0, so we skip that part. So we have 6 pi plus 18 pi squared over square root of 2. We round that off, we end up with 144.47. So you have your rounded answer and your exact answer depending on which one is asked for. Alright. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to our next subject, which is line integrals for vector fields. Alright. Line integrals of vector fields. Open that up a little. Okay, so what you want to do is you want to remember that work is equal to the dot product of your constant force and your distance from some point P to Q. Constant force. Of course, our distance is equal to point P to point Q, some distance there. Okay, so now I'm going to draw our three-dimensional graph here. We have our X, we have our Y, and our Z. And let me clean up that Z a little bit. There we go. Okay, now we're going to look at a three-dimensional curve starting at the origin. Let's say this curve kind of comes out and looks like that. Okay, so let's say if we have, for each point, let's say if we have the projection of the dot product of our force and our unit tangent vector. So if we have our force, it happens to be going this way. Of course, our unit tangent vector will be pulling that way. Okay, so the force in the direction of motion is the dot product of our force and our unit tangent vector times our tangent. All right, so in other words, since the dot product will give you a scalar multiple, that will just be an extension of your tangent. Okay, it doesn't have to be here. It can keep on going as you go through there. As you keep on going, that tangent can keep circulating. So what if we decide to just pick one little chunk of that curve to focus on instead of focusing on the whole thing? Okay, so if we pick that one little chunk to focus on, here you have your tangent vector. And of course, you have your scalar multiple, which will give you an extended version of that tangent vector. Now let's say if the little chunk we picked off, we call that S. So from here to here, that's just delta S for the change in S for that particular value. So let's say this is some S of I. This is some, what we call this S of I, and call this S of I minus 1. So that little chunk there is just some delta S. Okay, so you know that work is force and distance. We know the work needed for that one little section there. That will be almost equivalent to our force at that particular point. And the dot product of our tangent at that point. And our distance is, of course, our delta S at that particular point. Okay, so now the total work done would just be adding all of those little delta S's up. So our total work done, work will equal the integral of that dot product and our delta S, which of course is our ds. Okay. So remember, your unit tangent vector is equal to the derivative of your vector valued function divided by its magnitude. That's the integral of that. So your unit tangent vector, we can make that r prime of t over the magnitude of r prime of t. Remember, your ds, that's actually equal to the magnitude of r prime of t with respect to t. So of course these two are going to cancel each other out. So your work can be equal to your force and that dot product of r prime of t with respect to t. Okay. And of course, little side note here, derivative of r is equal to r prime of t with respect to t. So that means that our work can equal the integral of our force, the dot product of our force, with respect to our vector valued function. Right, which leads us all into a nice, neat little definition that we will put on the next page because we're running out of room. So if you're still writing, feel free to press pause. But we're going to go ahead and write down that definition. All right. So we have the definition of a line integral of a vector field, or usually used to find the work needed. All right, so what if we let our F be a continuous vector field defined on a smooth curve? Oops. And that curve, of course, we'll call C. And that's given by our vector valued function, which could be 2 dimensions or 3 dimensions, on the interval a less than or equal to t, less than or equal to b. All right. So the line integral of our vector field, I'll put that up there, on our curve is given by, okay, so we have your, I guess you can call this your general formula, which we know is equal to the dot product of your vector field and your tangent vector with respect to s. But the formula you're probably going to want to use, because it's a whole lot easier, from A to B, vector field at x of t, y of t, z of t, that and the dot product of your vector valued function, or your curve. Of course, this is 3 dimensions. If you have 2 dimensions, just x of t and y of t. I just figured instead of writing them both over and over again. All right. So first thing we're going to do is we're going to go ahead and evaluate. Then we're going to do a work problem. So if you're still writing, feel free to press pause. But we're going to go ahead and move on to our next example. All right, so what if we evaluate our integral for our vector valued function x squared y times your I unit vector plus x minus z times your j unit vector plus x, y, z times your k unit vector. Let me clean that k up a little. Okay, where your curve is represented by the vector valued function t times your I unit vector plus t squared times your j unit vector plus 2 times your k unit vector on the interval from 0 to 1. Alright, so just like before, you know our curve, t times the I vector plus t squared times the j vector plus 2 times your k vector. And the derivative is just equal to your, you can put 1 times the I vector, you don't have to, but I'll put it just to hold the space, plus 2t times the j vector, plus 0, with the derivative of a constant is 0, so you can put 0, but I'll just put plus 0 times the k vector, of course, just to hold the space. Alright, now just like before, your x of t, y of t, z of t, your x prime of t, y prime of t, and z prime of t. Alright, so that's why I put the 0 there, just kind of a placeholder. Alright, so we also know that our f of x, y, z, our vector field, is equal to x squared y times your I unit vector plus x minus z times your j unit vector plus x, y, z times your k unit vector. Alright, so plugging in our formula, you remember that the integral of the dot product is equal to the integral from a to b of our vector field, x of t, y of t, z of t, and that dot product of our derivative of our vector valued function for our curve with respect to t. Alright, so that, remember this is your x of t, so we have the integral from 0 to 1. Okay. So our f of x of t, y of t, z of t, remember you're going to replace the x with x of t, the y with y of t, and the z with z of t. Okay, so x squared becomes t squared times y. So you have t squared times t squared. So that would give you t to the 4th. Okay, so I'm just going to go ahead and write each of them out. So you have x squared, which is t squared, times y, which is t squared, times your I unit vector plus you have x minus z. So that's t minus 2 times your j unit vector plus x times y times z. So you have t times t squared times 2 times your j unit vector. Your k unit vector. Okay, so you have that, and the dot product of your derivative of your curve, which is 1i plus 2tj plus 0k. Of course, that's with respect to t. Again, that's a bad habit starting so far in that I have to try and squeeze it in. Alright. Okay, so now if we simplify all of this, we go from 0 to 1, of course that's t to the 4th times your I unit vector plus, we'll see that is t minus 2 times your j unit vector plus 2t to the 3rd times your k unit vector. Okay, remember that's just a dot product. 1 plus 2t times j plus 0 times the k unit vector with respect to t. Alright? Okay, now remember, with your dot product, you're going to get the first terms, multiply them, and you're going to plus the second terms when you multiply them, plus the third terms when you multiply them. Okay, so that's the integral from 0 to 1. So you have t to the 4th times 1, which is t to the 4th, plus you have t minus 2 times 2t. That's going to give you 2t squared minus 4t. Okay, so that's plus 2t to the 3rd times 0 is just 0, so really we can leave that out of there. We don't have to put plus 0. Okay, and that's with respect to t. Okay, so now we just go ahead and integrate. Okay, so you have t to the 5th over 5, or 1/5 t to the 5th, plus you have t to the 3rd over 3, so 2/3 t to the 3rd. You have t squared over 2 times 4, so that would be negative 2t squared after you simplify it. And that's from 0 to 1. Alright, so plug in your 1. Of course, you get 1/5 plus 2/3 minus 2. You plug in 0, you get all 0, so you don't need to do that. Okay, so we go ahead and simplify that. 15 plus 10 over 15 minus 30 over 15 will equal negative 17 over 15. Alright, so a little bit of work there, but still the same general idea. Okay, so if you're still writing, feel free to press pause. I'm going to show you one more form that your questions may come in. Okay, and that's the line integrals in differential form. Alright, so, of course, what if we let our vector field equals m times some I vector, n times some j vector, and your vector value function is, of course, your x of t times your I unit vector plus y of t times your j unit vector. Okay, so we already know that the integral of the dot product and the derivative of the vector field and the derivative of our curve is equal to the dot product using the chain rule. We just add our dt and dt, of course, that would cancel out. Okay. Now your dr dt, the integral from a to b, we can just replace our vector here with our formula. So we have m times the I unit vector plus n times the j unit vector. And that dot product, our dr dt, remember that's just the derivative there. So that can be replaced with x prime of t times your I unit vector plus y prime of t times your j unit vector. And our dt. Now remember, with your dot product, you multiply the first terms, you multiply the second terms. That's the integral from a to b. Okay, so you have m times x prime of t, I unit vector, plus n times y prime of t times your j unit vector. Of course, that's with respect to t. Okay. Now we know from our differentials that dx is equal to x prime of t with respect to t, and dy is equal to y prime of t with respect to t. Okay. Of course, our dt is right here. Just distributes the same way the integrals distribute. That's the integral from a to b, mdx plus n dy, which is what you would see for 2 dimensions. Of course, it would expand pretty much the same way for 3 dimensions. So the integral from a to b, mdx plus n dy plus t with respect to z. That's how it would be in 3 dimensions. All right. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to our last example, which will cover finding the work, but it will be in this form. Okay, so let's say, for example, we want to find the work done by the force field f of x, y is equal to 2x times the I unit vector plus y times the j unit vector on an object moving counterclockwise along a path C. Counterclockwise along a path C. Not where, but around the triangle with vertices 0, 0, 1, 0, and 1, 1. That's my little ampersand there. I'm running out of space. Alright, so, of course, with something like this, it helps to visualize by drawing a picture. And for a triangle, it's a pretty easy picture for us to draw. Okay, so this is our 0, 0. This is our point 1, 0. And of course, this is our point 1, 1. There we go. Okay. And we're going counterclockwise, so we're going in this direction. Okay, so we're going to call this C1, C2, C3. Okay, so what we're going to do is we're going to figure out the work to go from this point to this point, then the work from this point to this point, then the work from this point to this point, then add all three of them together. Okay, it can work with triangles, squares, any collection of lines. Okay, so we know that the integral to find our work, we can use that formula. Okay, but using the differential form, we know that's the integral from a to b, m dx plus n dy. Okay, so we know that this right here, that's our m, and this is our n. Okay, so you have our m and n, we just go ahead and plug it right on in. Okay, so the integral from a to b, so we have 2x dx plus y dy. Okay, so first, we're going to look at from the integral from 0, 0 to 1, 0. Okay, so know that x is from 0 to 1. In this case, y is just equal to 0. Y is 0 on both of them. X goes from 0 to 1. Okay, so really, since y is equal to 0, you just have to find the integral from 0 to 1 for our 2x dx. Okay, which is x squared over 2. The 2's cancel. 0 to 1. So we have 1 here for our work. Okay. So here, for x equals 1, you have x, the amount of work done. X is still 1 here, but for y, it increases from 0 to 1. So for our second interval, and y increases from, there we go, y equals 0 to y equals 1. Okay, our x is a constant, so there's no work involved staying in the same place. But for our y, we're going from 0 to 1. So that's the integral from 0 to 1, our y dy. Okay, so that's going to be y squared over 2 from 0 to 1. So that's going to be 1 squared over 2 minus 0 squared over 2, or just 1/2. Okay, so we figured out the amount of work needed to go here. Now, we need to figure out the amount of work needed to go in this direction. Okay, so we can actually figure out the formula here. We can see that's just y is equal to x. Okay, which means that your dy is equal to dx. Okay. And what do we also know? We know that x decreases from 0 to 1 and y decreases from 0 to 1. I mean 1 to 0. All right. Now, the thing is, well, the good part about it is y is equal to x, which means since we know we're going from 1 to 0, our integral is going to be from 1 to 0. Okay. Of 2x dx plus, remember, y is equal to x and dy is equal to dx. So we can just make that x dx. Okay, so if we go ahead and integrate, we have x squared over 2, which is just x squared, plus that just becomes x squared over 2 from 1 to 0. Because remember, you're going counterclockwise. Let me bring that down just a little. Okay, so if you're going counterclockwise, you're going from 1 to 0. Now, if they said clockwise, then we'd be going this way. But counterclockwise, we're going around that way. Okay, that's why we're going from 1 to 0 instead of from 0 to 1. Okay, so if we plug in 0, of course, we get 0. We have 0 plus 0 minus, plug in 1, get 1 plus 1 half. Okay, so you get negative 3 over 2 here. Okay, so we know the work done on each interval. Let's find the total work. We just add all of them together. You have 1 plus 1 half minus 3 over 2, which, oddly enough, is equal to 0. There's 0 work done. Okay, now it won't always be 0, of course. This is just for this problem. But problems like this are pretty much solved the same way. All right, so hopefully this made sense, and I will see you on the next video.